Oh, you're a little choppy. Can you hear me okay?
Professor?
Yeah, I can hear you now. Can you hear me all right?
Professor, can you hear me?
Yeah, I can hear you. Can you hear me at all?
Yes.
Okay.
Professor, I don't know what's wrong with the Logitech camera. It's on, but Zoom doesn't give me an option to select it. So
Okay, what does that mean? Does that mean that they can't see what I'm sharing or just that?
no, it just means you can't see you won't
Oh,
be
that's
able to.
fine. That's fine. All right, so are we good to go?
Yep.
All right. So hello, good morning, everybody. I hope you're doing well and you had a nice break. Couple quick announcements. So I sent out an email yesterday with the details of sort of what's remaining for the course. So we have a couple mini quizzes left. We have the chapter 5 quiz, and then there's an optional final exam. So you can read about that in the email. And you will be able to make a decision about whether or not you want to take it. Again, it's completely optional. You don't have to take it, so it's really just up to you. Other than that, there's going to be a review on Thursday and then again next Monday for the chapter 5 review to prepare for the chapter 5 exam that William will give. And I will send an email out about that tomorrow. So we are kind of just plugging along in chapter 5. So I'm going to go ahead and switch over to the doc cam. I'm just going to turn off my face video, I think, for the bandwidth here. I think it works a little bit better. Okay. So, last time we were talking about area under a curve. And so we were using rectangles to try to approximate the area under the curve. And so we had a left-hand estimate and we had a right-hand estimate. We said one was going to be an over and one was going to be an under. And so we did this with tables, we did this with functions, we looked at it with pictures. And so the last piece that we didn't get to is we want to generalize this. And so the way we generalize this is with something called Riemann sums. Okay, and Riemann sums are somewhat conceptual. And so we really have to think about what each of these pieces means when we talk about setting it up and what the notation might look like. So one of the key things that we need to remember is that we have this relationship between delta t, b, a, and n. So just as a reminder, a and b are endpoints. Okay, so where we start and where we end. N is the number of rectangles that we're using to approximate. And delta T is the width of one rectangle, which is also what we're counting by to get from our first endpoint to our last endpoint, right? So sometimes if delta T was say 4, that means we'd be counting by 4s, right? But that also gives us the width of the rectangle we're using to approximate. So that's what we had before. So now what we want to do is we want to try to generalize this idea of area under the curve, okay? And so we're going to do this in two ways. We're going to do this with a left-hand approximation, and we're also going to do this with a right-hand approximation. And I know that this is a left-hand approximation because you'll notice that it's the left-hand corner of each rectangle that is touching my function, which means that it's the leftmost rate that I'm choosing for each possible interval. Okay, and we talked about that last time a little bit. So if we want to generalize this, that means we want to be able to use what we're doing for any function. So we're going to call this function just f of t, a generic function here. And so some of the important parts that we need to make sure we understand are how we label them. So we said that A is our starting point and B is our ending point. And we need a way to index the values between A and B generically, right? So normally we'd be probably counting by like 1s or 2s or 3s, but we want to be able to count for any value. So what we do when we index is we do t sub 0, t sub 1, t sub 2, and then over here, this will be t sub n, right? So there's any number of rectangles hypothetically in between. Now, obviously in this picture, there are 4. There are 4 rectangles. But what we're trying to do is imagine that we could have had a lot more in there, right? So we call this last point t sub n to sort of indicate the number of rectangles we are using. Quite literally here it's 4, but we're trying to sort of expand our mindset and say, okay, we could have any number of rectangles under our curve, right? We talked about how we could add more by making delta t smaller. Now, the other piece of information, so remember, we're finding the areas of each of these rectangles and adding them up whenever we do rate times time, right? Delta t times the rate on the left, delta t times the rate on the left, delta t times the rate on the left. Well, the rate on the left is given by the height of this rectangle. And so again, if we're representing it sort of in a general way, when we look at the first rectangle, it's the t sub 0 that gets plugged into our function to give us the height. So we represent that height by f of t sub 0, okay? Now, similarly, if we're looking at the right-hand approximation, again, we're doing this in general. So we have f of t. We still have our same starting and ending point. And we still need our index here to talk about these different possible values. But the main difference we see so far is that when we talk about the height of the rectangle, with a right-hand approximation, we're using the righter point of the two that make up this rectangle. So instead of t sub 0, we're going to be using t sub 1 to get that height. Okay. So now what does it look like when we actually do a left and a right-hand sum in this sort of generic way? So one of the things I want to remind you, delta t is what we're counting by, and it's the width of each rectangle, which means that the width of every single rectangle here is delta t, delta t, delta t. So let's start with the left-hand approximation. If we want to get the area of this first rectangle, which we'll call number 1, we are going to do width times height, right? So the width is delta t. That's how far across it is. And the height is this f of t sub 0. It's the y value that we get when you plug in t sub 0. So that's the very first area. The second area Again, we're going to do width, which is delta t. Now to get the height, we pick the point on the left between the two because we're doing a left-hand approximation, so t sub 1, and plug that into the function to get the height. So times f of t sub 1. Now remember, we're trying to imagine that we can put in as many rectangles as we want. So we're going to do plus dot 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 plus, and then jump to the very last rectangle, okay? Now, again, we know there's only 4 in the picture, but we're going to pretend that there's n rectangles. So this is the very last one. So maybe there's 10, maybe there's 20, however many we put in. Whatever this last rectangle is, the width is still delta t. And the way we represent the height of the last rectangle, we would need this particular connotation, this little subscript. So what we want to look at, we know the last one is t sub n. So the one before it is t sub n minus 1. Right? That's the one before the last one, which means that this height is f of t sub n minus 1. So this is how we write a left-hand sum in a generalized way. What I want you to notice is that when we do this, every single term has a delta t because they all have the same width. What's changing is the subscript here, and that we never use t sub n because it's a left-hand sum. We don't use the rightmost rate, which is t sub n. Okay, now if we do the same thing for the right-hand estimation, let's look at this first rectangle. So again, the width is delta t, and now the height we get by plugging in t sub 1, right? The right hand of the 2 points. So delta t times f of t sub 1 plus, now the second one, delta t times f of t sub. Now again, we're choosing between t sub 1 and t sub 2. We pick the one on the right, f of t sub 2 plus dot 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 plus. We jump to the last one, which we're calling the nth rectangle, and we have delta t times f of t sub n. Okay, so this in itself is already a representation of how we can write this generically. However, as you can imagine, if we had 100 rectangles underneath, a curve, we don't want to write out 100 terms, right? If we have 4 rectangles, it's not so bad. But the more rectangles you fit in, the more complicated it gets. So we do have a way to notate this using what's called summation notation. And so you've probably seen this at some point in your mathematical career, but it may have been a long time. But so we're going to go over it. And the idea is that we have this symbol for when we're adding up a lot of the same types of things. So we're going to start with the left-hand approximation and talk about how we can write this mathematically. So we use this symbol. It looks like a curvy E a little bit. And this is for summation notation. And what that says is that we're going to add up a lot of similar things. And so what we want to do is we want to look at the terms of the left-hand approximation and see what is the same and what is different. So every single term has a delta t. Every single term has an f. Every single term has an f of t sub something. But what's changing is this subscript right here, right? So we see it's 0 and then 1, and then it keeps going. So we put what's called an index there, t sub I. And so what this does is we have to define where I starts and where I ends. So here my first I was 0. And my last one was n minus 1. So what this does is it says fill in I equals 0 plus, and then it'll go 1, 2, 3, 4. It'll keep adding up these terms until it reaches n minus 1, right? So that's the same as what we wrote out here, but this is a more efficient notation. And this is going to be helpful for us in a few minutes when we sort of talk about what this is going to lead into. So let's do the same thing for a right-hand approximation. again, we want summation notation. Delta t is the same. And again, we're going to do f of t sub I. The difference with the right-hand sum is that now we're starting at 1 and we're going to n. So I equals 1 to n. So that is the difference between the right and the left-hand sum, is this index. The left starts at 0 and goes to n minus 1, whereas the right hand starts at 1 and goes until n. Okay, so what do we do with this? Well, I want you to think back to what we talked about in the last class we had before this, where we said, okay, if delta t is smaller, so the width of each rectangle is smaller, that means we can fit more rectangles in, which means n gets bigger. And we said, and we did with an example, that if n gets bigger, our approximation gets better. Okay, that's sort of the main point we need to use here. If n gets bigger, our approximation gets better. So what does that mean? So we're still looking between A and B, but instead of 4 rectangles, maybe we have 8, right? So we only go half as far before we go up. Or maybe we have 16, or maybe we have 32, right? Still between A and B. But the more rectangles we have, the better our approximation, right? Our overestimate came down, our underestimate came up. So we use that with this idea that links back to chapter 2 of limits. If we let n go to infinity, so we're putting in 16 rectangles, then 32, then 64, then 100. So we're letting n get bigger and bigger. We're packing in more and more rectangles. That means the width is getting smaller and smaller. What will eventually happen is that the underestimate will come up, the overestimate will come down, and eventually they will be the same. Okay, so when the left-hand Riemann sum equals the right-hand Riemann sum, what has happened is that we have found the exact area under the curve. Okay, so this links back, right? Where last time we were looking for overestimates and underestimates from our left and our right. If our overestimate is the same as our underestimate, that has to be the exact area under the curve, right? So if I say the exact area has to be between 10 and 10, it's got to be 10. So when they match, when the left and the right are the same, we end up with the exact area under the curve. And when that happens, we get something special, which is called the definite integral. Okay, so that's where we're sort of moving to next. Okay, so hold that idea in your brain for a minute. Okay, so this was just a reminder. That's what we just did. But if the limit as n goes to infinity of the left-hand area is the same as the right-hand area, we get what's called the definite integral, which looks like this. Okay, now the definite integral, what does that tell us? This gives us area under the curve. Okay, it gives us the exact area under the curve. So remember, we are measuring area under the curve to tell us how much the original function changes, right? So A and B are still our endpoints. Okay, so they tell us between what two independent values we are looking for this area. Okay, f of t is the function that we are looking underneath, right? So this is a function where we're trying to get the area under the curve. Now, we have what's called the integrand. I'll trace that in blue a little bit. and the dt. Okay, so these are operators. Okay, now what does that mean? So addition is an operator. If I said 3 plus 4 equals 7, you don't say where does the plus go, because the plus is something that tells you what to do with the numbers. These are like bookends that tell you something to do. This bookend says find the area under the curve. This bookend says with respect to the variable t. Okay, what does that mean? So our function is being defined in terms of t. So we might have something like t cubed. This just says the variable is t. So all it does is it matches the variable here. Now, why do we need that? Because if you go on to Calculus 2 and you do further mathematics, it turns out you can do this with multivariable functions. So functions that have more than one variable. And this is going to tell you which one you are looking at. So while it doesn't have a whole lot of impact in Calculus 1, we have to have the same convention so that when you do expand to higher level mathematics, we are able to follow the steps. So once we've calculated the area, we get some sort of number on the other side. Okay, for example, if t is in hours of a 20-hour period, the rate at which the bacteria population is growing is given by f of t equals 3 plus 0.1 t squared. This is the exact function we worked on last class, and we did this with delta t equals 4, and we did an approximation. But now that we know how to think more about this in this term, we want to find the total change in bacteria over this period. So if we have this notation, we are looking for the exact area under the curve, okay? And so when delta t equals 4, so when we did this approximation before, we found that we had to be between 252 and 412 bacteria. So that was last time. So you can look back in your notes if you want, but we approximated this with a table. But now if we want to find the exact area under the curve, how do we actually do it? We know that this notation means to find the exact area under the curve, but what are the steps we have to take to do it? Well, for right now, as we look at area under the curve, we are going to do this with a calculator or a computer. Okay, so I'm going to show you how I enter this on my calculator. If you have a similar calculator, it will likely be the same way. If you don't, you may need to Google your calculator name plus definite integral, and you'll find the instructions. So here is my calculator. And so what I do when I want to do an integral is I go to the math button, which is right here, like that. And I have to go down to the 9th option, okay, which says FNINT. I can also push the number 9, or I can scroll down and hit enter. On my calculator, it sets up an integral for me that looks like this, where I'm filling in different values. So I have 0 on the bottom, then I hit the up button, I fill in a 20 up on the top. Then I come into the parentheses, and this is where I'm going to fill in my function. So that's the 3 plus 0.1. Now here, you see on my paper, it's t squared. I could change the variable, but I'm just going to use x instead of t because it represents the same function. So I'm using this variable button right here, xt theta. So when I do that, it puts in an x, and then I'm going to push my squared button. And then I have to come over here to the end, and my variable has to match the operator at the end. So since I used x, I put in dx. I hit enter. Sometimes this can take a few minutes, depending on your function. Oh, I have a typo in the notes. So this should be 326.6. I don't know why I wrote 307. So it's 327. 326.6 rounds to 327. So that's how we enter things into the calculator. If you have a TI-83 or an older version, When you get to the ninth option, it may look like that on your calculator. It may just say FNINT. And so the way that you enter it, doing it that way, is you enter the function first. So you would enter 3 plus 0.1 x squared. Then it's like essentially the operator at the end. So then an x, and then the lower bound, and then the upper bound, and then close parentheses, and then hit enter, and it'll spit out the 326.6. So we have to practice putting some of these things in our calculators, or again, you can use a computer on your phone. You can use like Wolfram Alpha or whatever you need. But for right now, we do have to do this on some sort of computing device. So let's look at an example 1 here. If you have your calculator on you, you can go ahead and take it out. If you don't, but you have a phone, you can certainly use like Wolfram Alpha. But I want you to try to calculate the area under this curve between 0 and 3. And so syntactically, we're looking from 0 to 3. Our function is x squared plus 3x plus 1 dx. Okay, so I'm going to give you about a minute and a half to try to figure out how to put that into your calculator if you have it, or use your phone to navigate to, like I said, either Wolfram Alpha or another computing website to try to find this area under the curve, and then we'll go through it together. So take 1.5 minutes and try that out. Okay, take about 30 more seconds. Okay, so I'm going to show you how I entered this on my calculator, just so you can make sure the syntax looks the same on yours. So the integral from 0 to 3, and then we have x squared plus 3x plus 1. And then again, we have to add the same variable that we were using here, and I was using x. And then I hit enter, and it spits out the area under the curve. So it's 25.5. So again, what this number is telling me is if I were to graph this function, this is the function I'm interested in, this would tell me the area underneath the curve from 0 to 3. So it would be the same as if we had drawn in enough of those rectangles where the overestimate and underestimate approach the same thing. Eventually, we would come to 25.5. So now we need to talk about how the stuff that we had learned last class and this idea of the exact area under the curve sort of intersect. So we see this in a couple different ways, and we have to be really careful to read instructions of every problem and figure out which tools we have to actually answer the question. And so sometimes it's easy to sort of get tricked in what you're actually looking for. So we're going to try a couple practice problems here where we just want to be careful, you know, with the instructions to figure out what we're doing. So we'll look at example 2 and 3 here. So example 2 says values for a function f of t are given in the table below. Estimate the area under the curve from 10 to 20 of f of t dt. So I want you to think about what we know from before and what we know from today to figure out how we might answer this question. And then for example 3, the graph of f of t is given below. Use n equals 1 to determine bounds for the area under the curve from 1 to 3 f of t dt. What do bounds mean? So that's the upper bound and the lower bound of what the actual area is. So an overestimate and an underestimate. Okay, so I want you to take about 2, maybe 3 minutes, try out these 2 problems. Even though they have definite integrals in them, we need to link this back to what we were doing last time to actually answer the questions. Okay, so try it out. I'll give you about 3 minutes and then we'll go through it together. Okay, take about 30 more seconds. All right. So again, we have to be a little careful and make sure we read the question and use context clues to figure out how we can answer this. So the first thing I want to draw your attention to in example 2 is this word estimate, right? So that gives us a clue that we're not actually finding the exact area under the curve. We are trying to approximate the area under the curve. So even though we have the integral here, we can't find the exact area under the curve. We don't actually have the function. So the only thing we can do here is estimate. The next thing I want to point out is that the bounds on the integral are telling us where we are trying to look. We are interested in the area between 10 and 20, which means we're not using the whole table, but instead just the parts between 10 and 20. So now that we have that figured out, we want to approximate the area under the curve between 10 and 20. The best we can do right now is what we were doing before. We can look at a left-hand estimate a right-hand estimate, and then from that, a best estimate. Those are the estimates we can get here. So if we were to do a left-hand estimate, remember for each time interval, we're going to fix that time interval by delta t here equals 5, because we're counting by 5s. And for each time interval, I'm going to pick the rate on the left for a left-hand estimate. So here from the first time interval, I'm going to pick 42. So 42 times 5 plus. Now from my second interval, I pick the one on the left, which is 51 times 5. Okay, so I'm going to add those up, and I'm going to get 465. But I could also do a right-hand estimate where each interval I pick the rate on the right. So now from the first one, I would pick 51 times 5 plus, now I pick the one on the right, which is 60 times 5. I add that up and I get 555. If I wanted to do a best estimate, I would average these two. 555 plus 465 divided by 2, and I would get 510. All of these are appropriate estimates for the area under the curve. On homework or a quiz, it'll say, using a left-hand estimate, using a right-hand estimate, or find the best estimate. But these all give an estimate of this area under the curve. So even though we have an integral here, a definite integral, which indicates the exact area under the curve, it's actually just asking you to approximate that area given that we have a table. Okay, example 2 is sort of similar, but now we have a graph. We want to use n equals 1 to determine bounds for the area between 1 and 3. So let's figure out where 1 and 3 are here. Okay, so again, the endpoints are giving us important information about what we're approximating. So n equals 1 means that we're going to have one rectangle to approximate this area. So again, we can do a left hand or a right hand. So let's do the left hand first. So for a left hand approximation, I'm going to use the height from the left hand value. So from the 1. So I go up till I hit the curve, and that becomes my height for my rectangle. Okay, so the left-hand point on the rectangle touches the curve. So here, if I want to get the area from 1 to 3, that has a width of 2, and then we have a height of 2, and 2 times 2 is going to give me an area of 4 when I do a left-hand approximation. Okay. But I could also do a right-hand estimation. And if I were to do a right-hand estimation, I'm going to get the height by picking the value on the right. So it's about here. So again, the width is still 2, but now the height is approximately 1. So 2 times 1 gives me an area of 2 as a right-hand estimate. And the question asked to determine the bounds. And so how I would answer this question is that the exact area under the curve has to be between 2 is my lower estimate and 4 is my overestimate. So it's got to be between 2 and 4. Those are the bounds where the actual area needs to be. And again, the actual area is the area under the curve that's here that we're trying to approximate. Okay, so again, we couldn't get the exact area under the curve because we didn't have the function to plug in. Instead, it said use n equals 1, which leads us to believe we're doing an estimate. And again, we're using what we know from before. Okay, so those are times where the integral shows up, but we're not actually computing the integral. But there are plenty of times where the integral shows up and we are computing the integral. So we're going to do a couple of those. So the first one is just sort of a generic getting used to plugging things in and making sure our settings are correct. So for this problem, I want you to spend about 2 minutes, and I want you to find the exact area under the curve for each of these functions, because I just want you to get used to plugging things in. I want to remind you that your calculator should be set to radians, or if you're using a computer, make sure it's computing in radians to find answers here. Okay, so take about 2 minutes, find those areas under the curve, then I'll tell you what I got. Hopefully it's the same thing, and then we'll look at some more word problems. Okay, let's take about 30 more seconds. All right. So I'm just going to write down the solutions that I got. If they don't match yours, I would strongly encourage you to stop by Drop and Help with either me or the TAs to review how to enter things correctly, because oftentimes it's just a matter of like parenthesis placement or something small that can be adjusted on your calculator or your computer settings. So it's typically just like a parenthesis that has gone rogue in some way. But you should be getting areas that look roughly like this. So hopefully, you know, plugging things into your calculator is starting to feel a little more normal and you get used to the syntax. Okay, so let's look at a word problem and see if we can figure out how to apply what we're learning to this particular problem. Okay. So example 5, let's see. Sorry, I went on to 2 pages here. So it is important for pharmaceutical companies to test the characteristics of drugs they design. The strength of the drug is given by R of M, where M measures the dosage, i.e. the amount of medicine absorbed in the blood. Suppose an experimental drug changes a patient's temperature at the rate of R of M equals 3m squared over m cubed plus 1 degrees per milligram of the drug. Find the total change in temperature resulting from the first 4 milligrams of the drug. So I'm just going to write this function a little bit bigger in case you can't see it. So 3m squared over m cubed plus 1. And again, this is the rate at which the drug changes your temperature. So if we're looking for the total change in temperature, we need to find the area under this curve. So I'm going to give you about 2 minutes to think about how to set this up, how to calculate it, see if you can figure it out, and then we will go through it together. Okay, take about 30 more seconds to finish up whatever part you're working on. All right. So I want to remind you that when you see the word total, that typically means we're looking for area under the curve, because the rate that we're given is going to help us understand how much the original function changes. So here the original function is temperature, and the rate is given in degrees per milligram. So how quickly the temperature is changing based on the amount of drug. So we're looking for the total change of the first 4 milligrams. So when you say first 4, that means we're going from 0 to 4. So we're going to be integrating this function from 0 to 4. And if we want to set this up as an integral, this would be dm, because again, the variable here has to match whatever the variable is here. This is just telling us what the variable is. So now that we have this, we would figure out a way to enter this in our calculator. And again, you can certainly turn your m's into x's to get the same value, but you need to make sure your bounds are 0 to 4. And when we enter this in, we will get 4.17. So that means the total change in temperature is 4.17 degrees. We don't know this person's temperature because we don't know what their temperature started as. All we know is that it changed by 4.17 degrees. And since it's positive, we know that that change was that the temperature went up. But we don't know what their temperature was because, again, we didn't know their starting temperature. If we knew how much their temperature was to begin with, we could just add the 4.17 to it. But all we can find right now is the total change. Okay. So let's look at one more example here of this type of problem. Okay, and this is about the greenhouse effect. I'm going to have you try this out, where we are trying to use the rate at which the temperature is changing to determine what we think that the temperature of the Earth's surface, the average temperature, will be in 2200, 2300, and 2400. So just so I'm going to write the rate a little bit bigger in case you can't see it. So that's the rate we're looking at. And I want to remind you, T is going to be in the number of years since the year 2000. So as you read this and you think about the bounds that you're going to set up your integrals for, remember that reference point. Okay, so take a look at this, try it out. I'm going to give you about 3 minutes because you're going to do 3 different predictions here, and then we will go through it together. Okay, take about 30 more seconds. All right. So since T is the number of years since the year 2000, when we look at part A, we're interested in what happens between the year 2000 and the year 2200. So we're trying to figure out the total change over those 200 years. So from T equals 0 to T equals 200. And if we were to set up the definite integral for this particular rate, it's going to show us how much the temperature changes. So when we calculate that number, if you put that into your calculator, you're going to get 16.65. So that's the change in temperature. Now, we know that the average temperature was 57.8 degrees to begin with. So we actually do have some initial information here. So if we're trying to predict the temperature in 2200, we need to take the average temperature and add on the amount that it changed by. So we have to add on the initial temperature to make our prediction. And when we add those together, our prediction is going to be 74.45 degrees, okay, for the average temperature of the Earth's surface. Similarly, if we want to predict the temperature in 2300, we need to see how much the temperature is going to change over 300 years, if this is the rate at which the temperature is changing. And so when we plug that in, we get 29.37. But again, that's how much it changes over 300 years. We have to add in the fact that at our starting point, we were already at 57.8 degrees. And we get a new prediction of 87.17 degrees as the temperature of the Earth, the average temperature of the Earth's surface. And then finally, over 400 years, we go from 0 to 400. We plug that in. We find that the temperature will change by 43.94 degrees. But again, we have to look at that in relation to where we started, which was 57.8 degrees. We add those together, and we get 101.74 degrees. So again, when you're given some sort of rate and we're looking at how much the original function changes, that tells us that we're looking for area under the curve. If we have the function, we can use definite integrals to get our exact area under the curve. But if we have tables or other types of things, sometimes we do need to approximate. Okay, so the next thing we need to talk about is the fact that everything we've sort of looked at so far has given us positive outcomes, which is not always the case. Okay. And so we need to think about what the definite integral actually tells us about area, right? So we're using these words, area under the curve, right? And we've talked about area in past math classes. So if you think about the area of a rectangle, it's base times height. The area of a triangle, 1/2 base times height, right? So this concept of area should hopefully be sort of in your mind of what we're talking about. So what we've looked at so far is instances where our function is strictly above the x-axis. So we're looking at things like, like this, right? And when that happens and we're doing our rectangles to try to approximate, right? All of these rectangles have positive area because we know that rectangles in general are base times height. And when we've considered this in the past, we haven't oriented it into a specific space, okay? So if we were thinking about something like the function x squared, Okay. So x squared is a parabola. It looks like this, right? If we look at the area under the curve, again, any area that we find, even if it's exact, is above the x-axis. So the idea is that the area we are finding is the area between the function and the x-axis. Okay, so that's what we've been doing so far. And we've been doing it sort of pretty convincingly that this might be the way at which we do this all the time. However, it's not. So we're going to look at a couple of examples and then talk about what this particular thing might mean. Okay, so example 1, the rate at which your income is changing is given by 1.85 to the T in dollars per month, where time is in months. Find your change in income during your first year working. Okay, so I want you to take 2 minutes, and this is an example of a positive outcome. You should get a positive number. Think about the units here and how you would set up this integral. Okay, so this is what we were doing before. We're thinking about how to set up the integral, and then we'll go ahead and talk about another example after, but go ahead and take, I don't know, 1.5 minutes, see if you can set that up and find that area. Okay, take about 30 more seconds. Okay, so if we were going to set up this integral, there's 2 important things that we sort of have to figure out here. The first is that we're even setting up an integral to find area under the curve. We sort of have a clue of that since it's the section we're working in. But the other part is the bounds, okay? So the rate is in dollars per month, and we want to find your change in income during the first year. So we have to convert the bounds from 1 year into months, since the rate is given in months. So this is going to be from 0 to 12. And again, this is another function where if you were to graph it, so I'm going to show you what the picture looks like real quick. This function is above the x-axis, right? It's positive. So we are expecting the area that we get out of here to be positive. So the syntax on this looks like this. I use 0 to 12. I use the x instead. When you do things that are exponential, it takes a little bit longer than polynomials. But here we get $2,610.86. Okay, so we're talking about income. So this is money. So we'll round to 2 decimal places. Okay. So all is good. This is in line with what we've been doing. We have these nice positive things. Now, if we were to calculate the integral from -1 to 1 of x squared minus 1, this is where things start to get a little more complicated. So if you have a calculator, you can go ahead and enter it there. I'm going to quickly enter it into my calculator so I can show you. Okay. So I have the integral from -1 to 1 of x squared minus 1 dx. When I push my enter button, I get -1.33333, so -4/3. Okay, this is the first time we've encountered something that is negative, and we need to talk about what that means, why it's okay in this context, and how we look out for this as we're doing different problems. Okay, so I'm guessing at this point in your life, unless you've taken calculus before, you haven't dealt with negative area, right? Because when you think about triangles, if I said the area of the triangle is -5, you'd be like, what does that even mean? It doesn't mean anything outside the specific context of what we're looking at, right? So negative areas don't make sense to us yet, or at least to me. Okay, so x squared minus 1 looks like this. And this is the point of 1, and this is the point of -1. So when we talk about the area under the curve, right? So remember from before, we're looking between the curve and the x-axis. What's different here is that this area is below the x-axis. Okay, now, if we were not in calculus, if we were in a geometry class and I was like, here's a function, here's a space, find some area, that area would be positive, right? Because the area represents the amount of space between functions, right? Or between specific points. But in calculus, what we have to remember is that we are looking at a rate, which is a derivative, to tell us about the original function. And we know that if the derivative was negative, so that's what's happening here, right? The rate is negative underneath, that the original function is decreasing. Okay, that's a relationship we had. So what that means is we need a way for us to talk about the fact that it's decreasing whenever we're below the x-axis. And the way that we do this in calculus is by counting the area underneath the curve when it's below the x-axis as negative, okay? And if you think back to our rectangles, let's say we're approximating some rectangles, right? How did we approximate them? We did delta t times f of, I don't know, say 0 to get this particular one here. Okay, well, f of 0 is a y value that is negative. So this is a negative value. And this is a width, so this is positive. Okay, so what's the takeaway here? Okay, 1, unless you are in calculus, area should just be positive. It represents something different. In calculus, when we talk about area, specifically area under the curve, where the area is helps us understand if the original function is increasing or decreasing in terms of total change, okay? Which means that for us, area underneath the x-axis is going to be negative, and area above the x-axis is going to be positive, okay? So this is different and sort of adding on to what we were doing before. Again, we were just looking at positive examples before. And so, you know, this idea that these rectangles, again, are going to give us negative area is specific to this context. So let's look at a quick example and see how we can apply what we just talked about. So the average daily temperature from October 1st until February 1st is declining at a rate of f of t equals negative 0.9 to the t degrees Fahrenheit per day. There are roughly 92 days between October 1st. Oh, I think that was supposed to say January and January. And January 1st, determine the change in temperature over this time period. Okay, so I think this one was supposed to be January. Sorry about that. So what we need to do is we need to integrate our rate, okay? And we're going to be integrating our rate negative 0.9 to the t dt over the 92 days. So 0 to 92. Notice that this is in days, the rate is in days, everything matches up. What's different here is the interpretation, okay? So when we plug this in, if you have a calculator, you can go ahead and plug it in. I'm gonna plug it into mine so I can show you again the syntax. Okay, so I put mine in like this. Let's see if it'll take that without any issues. My parentheses, notice that the negative is outside of the function. Oh, it didn't like that. So I have to change my parentheses. So let's see if that will do it. Didn't like my negative sign. Okay, so I have negative 9.49. So what does that mean, right? So now we have to start making sure that we understand the syntax as well as what it means to be negative. So that means that we are decreasing by 9.49 degrees. I think it's in Fahrenheit. Yes, degrees Fahrenheit. So we'll say degrees Fahrenheit. Okay, so the negative tells us that we are decreasing in the original function. So the original function, which is temperature, changes by 9.49 degrees and it decreases by 9.49 degrees. So if we had an initial temperature, we would do that temperature minus 9.49. Why does the negative area make sense? It makes sense because a lot of functions we look at increase and decrease, and we need a way to account for that. So what are the big takeaways? Area above the x-axis, positive. Area below the x-axis, negative. When we get results from the area under a curve, we look at whether they're positive or negative to determine if the original function was increasing or decreasing in total change. Okay, so we're going to stop here, and what we're going to look at next time is what happens if we have some area that's positive and some area that's negative. How do we deal with that, and how do we interpret those types of results? Okay, so try out some of this homework, and we will pick this up on Thursday.